Hey, we will get started. Good morning, all. So last week, or last week, Judah covered sessions on a session on which he did a lot of important ideas he discussed on biology. Just to add a little bit, so we all talked about Darwin. Darwin's evolution theory was an output of his voyage, right? At the age of 21, um, he was, or 22, something like that. He was, he entered into a voyage, which was a map drawing ship, right? It went through all these things, all these areas to draw the continent's maps. Darwin's father was a father wanted Darwin to become an engineer, but young Darwin did not have that kind of aptitude. He wanted to become, he was a biologist. So he observes species and wanted to get into biology. But somehow his father said that, okay, at least let him be useful to this, his friend who was the captain of a ship, who was about to go into some voyage. So he put Darwin into the ship and sent him, which actually turned Darwin's life. So this is a very funful fact that was not discussed uh, during the last discussions. I wanted to bring it up. So he took this voyage, and it was supposed to be a 2 years voyage. It completed after 5 years, going to a lot of different continents as shown in the figure, and come back with the Darwin collected a lot of species samples. And when during this voyage itself, Darwin came to a conclusion that species does not form in this particular form, it evolves, right? So Darwin came to the conclusion at the age of 25, 26 itself. But he published his book of Origin of Species only when he was here at the age of 40. He whatever probably he was afraid of church, or for whatever reasons he did not publish it. But as Judah pointed out, Wallace was again another young biologist, almost 10, 15 years younger than Darwin. He was about to he was about to publish because he also came to the conclusion. But then Darwin realized that it may be too late to if he doesn't publish. So he published it. So what he published is a book called Origin of Species. The book talks about two important things. One is it talks about that a species slowly changes and becomes another species over a period of long time, right? That happens with subjected to these two laws. One is the struggle for existence and the natural selection. So struggle for existence pushes the species to uh, to 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 use new strategies, right? When you have a when you run for life, you will become anyone who wants to survive will be fighting hard, right? So struggle for existence really drive this evolution. And while struggling like that, the species tries to get um, sometimes it gets new variations in its body, right? For example, let's say we have 100 cats and 100 rats, right? Say they are fighting each other for survive to survive in a particular given space. This 100 rats, for example, one or two rats got into some changes in its legs and got a longer leg. Let's say, okay. So over a period of some 2-3 months, these longer leg rats will be able to run faster, right? The shorter leg rats could have been caught by these cats, and over the period of time, these longer legged rats, which could have reproduced, right? It will reproduce and become all these rats, which were at 100, which when it reproduces, all these rats which were having shorter legs would have extinct. Only longer legs rats will survive, right? So the I'm just doing a super simplification here. So that is how this slowly an accumulated change in a body, it will help in surviving better, and that will be carried on to the next generation, which is kind of naturally selected. Not all changes will be carried on to the next generation. Some of the changes which are not useful will be probably die away, but those which are useful, if it is carried on to the next generation, slowly these accumulated changes will become a new species. So similarly, cat also has to, if cat does not change, it will starve, because all rats will be now overrun these cats, and and uh, uh, um, and it will have to starve. So that is how this has to also adapt. Maybe it has to run faster, or maybe it has to strategize to some other way. All these things is a kind of competition, which is for struggle for existence, and natural selection will transform the species to a newer and newer species, and that's how species evolve. So Darwin arrived at this conclusion and published this book with this specifying these two laws, explaining various samples. It's a good read, but little tough. I recommend trying it out if you have not done already. But apart from that, Darwin also published another book in 1871, on directly on. I mean, then people are asking whether how did man come. This is applicable to men also, or humans also. So he did a book on this, and specified something called, the book name was Descent of Man, and in that one he explains something called natural selection, sorry, sexual selection, how sex plays a role when selecting for breeding, right? I mean, selecting for mate. The a women, female sex tries to get the best male, so that it can produce the best surviving offspring, so for the survival. So he talks about various secondary sexual characters. They call it secondary sexual characters, like a beautiful horn of a cow, or a beautiful trunks of an elephant, or beautiful feathers of a peacock. That's all becomes a beautiful secondary sexual character, which drives the female to select that strong male, and get into mating and produce a new offspring. So that is also plays an important role in transferring the important characters to the next generation. So these are all kind of drives this evolution, and that is how species transform from one form to another, and that is what Darwin's um, origin of species gave. And of course, Judah already pointed out that how social Darwinism was a failure. So just wanted to quickly tell about that. Social Darwinism, sometimes people try to argue, right? When we talk about equality and all, people say that no, somebody, you see, so, Darwin himself told the evolution theory, survival of the fittest will exist, others will naturally go down, right? So they will try to apply to the society and say that if somebody is poor, he is not able to survive because he is not fit, or she is not fit. right? If that for those people, I usually give the argument like, for example, if somebody, our loved one, has some fever or some small issue, health issue, do we just let them be like that and allow them to see, or allow ourselves to see whether that individual is fit and they survive themselves? No, right? We just take them to doctor. Or if some strong person try to come and hit us, we just don't fight directly, right? We say we go to police, court, complain, and try to protect ourselves. So with these, all these factors, natural selection won't work, right? It's an artificial selection. So natural selection or struggle for existence, it has to be without interference through the natural process. So social Darwinism is a failure theory. Just be aware of it. I just wanted to make sure we all know that, so that we don't fall in the trap of using it, this theory in the society, which is very common. People used to say that. Okay. So this is something that I wanted to mention before going forward. So in our physics steps that we were following, we were talking about Einstein during that last session, but we didn't fully go through it. We wanted to continue that session and try to conclude it today. So Einstein's relativity was it's an answer to this experiment done by, there are several questions that it tries to answer, but importantly this Michelson-Morley experiment, which was conducted in 1887. The purpose of this experiment is like this. We told that there are waves, right? We talked about waves. Waves always, waves need a medium, right? When you throw a stone in the water, water waves go like this. Actually, water molecules go up and down like this, right? But the energy transforms like this. For example, if you put a small lid here or a plastic something which can float, you can see that it goes up and down. This bottle or lid itself does not move. But you know that wave is moving like this. The energy is transferred like this. The oscillation is going to the next molecule, next molecule, next molecule. So the energy is transformed like this, but the molecule itself actually moves. This is called transfer waves. And there's something called longitudinal waves, where the medium's particle oscillate like this in the direction of the wave. The wave goes like this. The oscillation also like this, in direction of the wave. That also, there's another type of wave. But whether it is transfer waves or longitudinal waves, we need something to oscillate, right? We need a medium. Waves need a medium. Now the question arises. Sun is here, Earth is here. We already saw that Maxwell told that light is wave. That fight is going on. We are in between the fight. There is Maxwell already told that electromagnetic waves and light is wave. So now the question comes, when sun emits light, that light is coming to Earth. What is oscillating here? What is the medium? They all thought that it's a vacuum, but now we need a medium here. The idea people used to describe this medium is there is something called an invisible liquid called ether. So that ether medium is there. But of course, no one knew what that ether medium looks like. They do not have any experimental evidence for this. So, but the ether medium is assumed, and they were light has to travel through this ether medium. That is how light, if light as a wave, would travel from sun to earth. So, and there is one more thing that is known already, is that when a body travels, say, let's say when an aeroplane goes like this and it drops a bomb, the bomb does not fall straight here, right? The bomb will also travel to some extent like this and drop here. The aeroplane's velocity and the bomb's velocity will be added and it will travel. It is called relative velocity. When it goes into the same direction, it will be added. When it goes in a different direction, it will be subtracted. We all know this from our +2 mathematics or science, right? Now, these guys, Michelson and Morley, took these ideas and wanted to check, okay, how light's velocity will differ based on the Earth's rotation, right? When Earth rotates in some direction, it will drag the ether as well. If ether is there, it will drag the ether as well. So when the ether is going like this, if you put a light source here and observe here, light's velocity should be addition of ether's velocity and light's original velocity, right? So it should be, say, let's say light's velocity is v, then it should be ether's velocity plus light's velocity, right? That is what they wanted to experiment. And then in the reverse direction, light's velocity should be less. They measured in all directions, and absolutely light's velocity is the 3 lakh kilometers per second, which was constant. In whichever direction they measured, they see that light velocity is constant. So that either sorry, I used this either spelling wrongly. So they concluded by these two experiments, they concluded that ether is not there, no ether, and velocity of light is constant on all direction. V equal to c in all directions, right? So now there is a conflict. Now how do we address it? Now it is when light is constant and there is no ether, how does light travel in the space? Okay. So again, light is it a particle? Particle does not need a medium to travel. So that is what actually Einstein's relativity, but the special relativity takes it and addresses it, right? So we saw these things already, I think, but then we'll just quickly try this again. So when Einstein published these three things. One is the photoelectric effect, which talks about that using this Planck's quantum idea, which was recently discovered in 1900. He used this and proved that light is particle. That means it bombards an electron in a metallic plate and discharges the electron. Light can discharge the electron and create an electric current. That is how photoelectric effect is coming. So light should be a particle, right? And of course, you know this, all of us know this mass energy relationship. And he also explained Brownian moment in this time, which is a confirmation of atomic theory. So this special theory of relativity also talks about, okay, velocity of light is in all direction is same. Now, so that predicts two things, not two, I mean, at least one important thing is not important thing. I mean, this is important paradox is that time dilation, right? You might have heard about all this time dilation. That is, time is slower for those who travel faster. Time elapses slower, time passes slower when you travel fast. So theory of relativity says that everything is relative. Your measurement is differs if depending on which direction you are traveling or related to what you are measuring, right? So it is completely destroys the absoluteness of anything. Only absolute thing theory of relativity agrees is on the speed of light, right? So light is always going in the same speed. So that's why this time dilation has to come. You have to use this. You have to accept this because when somebody is on the on a stationary tries to throw a ball like this, going up and down, right? Please let me know if it is too repetitive because you may have already studied these things. I'm just adding it, thinking it for a common people. So if you have already known, we can skip. Okay, if somebody stationary throws this light, throws a ball up and down, then he or she may say the ball cross this L length in 5 seconds. But if somebody is traveling like this, and he or she throws a ball, the for that person who is traveling, the ball will actually go like this, right? But a person who is observing from outside, it will travel like this, and by the time the person who throws the ball also will go like this, and he will catch it here, right? When you travel like this and catch it here, the person outside who is observing will say that the ball did not throw, the ball did not go travel the length L, but it will travel 2D, not 2L, not 2L, it is 2D length. So it has traveled faster. Sorry, it has traveled more distance. But you cannot, but the person who is internal in this, let's say it's a train or a ship, the person inside this ship, he will say that no, it went up, straight up and down, right? So, but for the external person, it travels 2 times the distance. Sorry, not just 2 times the length, it is 2 times D actually. D is more than L, right? From the picture itself, you can see. So the distance is more, we know that. Time taken according to the person who is traveling inside, he also will say that in 5 seconds, I caught the ball. Velocity of light is same, irrespective of all inertial frame of reference. I mean, irrespective of in which direction you are traveling, velocity of light same. So who is correct? Then this paradox has to be corrected by saying that the time itself slowed down here. The person who is traveling, time slows down. Okay. So that is how this time dilation comes. And this is experimentally verified by sending some particular material which has this rays. It emits that rays. Anything which emits particles or rays which will decay and it becomes half-life. It has a half-life period and it will decay to half during the during that time, right? So there's a period called half-life period. We saw some 2-3 sessions back. So they send such 1 gram of such particle, let us say, from the space. That's recently verified. So they received only half of it, and its half-life period is like 10 minutes or something like that. So you can be easily verified the time dilation. It is not just a person who is observing make mistakes. It is there naturally, and that's how they verified it. So this all came, and Einstein shattered a lot of things. People, all these things are published in 1905. So so again the problem of whether it's a wave or particle, the fight continues, right? So then Einstein continues, and the special theory of relativity is nothing but relativity without gravity. But then adding gravity, he came up with something called field theory of gravity. This is called the general theory of relativity, overthrows the absoluteness of space. So there is no absolute space, there is no absolute time. Space itself, and the appearance of space or the property of the space is different for different people based on where you are and how you are attracted to the gravitation, or is there a mass nearby. All these things defines your what to say, your space. Okay, so what that means is that, remember we asked one question sometime back. When Newton proposed the idea of gravity, when two objects attract each other, there is nothing in between, right? How can it attract? How can it attract or repel? There is nothing in between. It is like a action at a distance, like a magic. You cannot, science cannot accept these magics, right? It has to have some kind of explanation on how it actually happens. Newton does not have this idea. Newton did not have how to solve this, because during the Newton's time, everything was approached like in force. A physicist knows that force is only one form of solving or explaining a system. That is, in recently they all approach the system using energy, right, or field. During Newton's time, there was no field. After that, only the field idea. So to explain magnetism, the idea of field came. We already talked about that little bit. Field is nothing but area of influence, right? So what Einstein says is, when there is a mass, it influences this area around, like magnetism. It pulls that space around to a curvature. So the geometry of the space itself gets disturbed. This is a little bit difficult to understand or accept. Now people are able to accept, but when the time it was proposed, Einstein's theory was very difficult to accept, because space itself is deformed or curved, right? The geometrical description of the space, he took it and made a beautiful mathematics to explain his field theory of gravity. So whenever any particle travels here, like you travel in a curved road, you have to go in this direction only. You cannot say that I will go straight, right? If the road itself is curved, you have to turn your car or two-wheeler or whatever. Like that, when an object travels like this, it has to follow this curve. You cannot escape. So that is how gravity works. Gravity is nothing but the space itself is curved, and any object going through that space has to follow this curved surface. That is how the gravity works. So that is why this description of gravity is better description of Newton's gravity, better than Newton's way of describing gravity, because Newton's way appears like action at a distance, but Einstein's explanation is there is a field. Because of mass, the field is there. The field curves the space, and the objects traveling through the space has to go through this curve. That is what we feel it as gravity. So that is what Einstein proposed. The big thing is it completely shatters absoluteness. Okay. So for Newton, absoluteness is like God. Newton was a very strong believer. So the idea of absoluteness of time, space, and all is like, because of God, this absolute thing is there, but that is completely removed by Einstein's relativity. Any questions so far?
Just to add, you mentioned that force, the concept of using force was dominating for a long time before field concept or energy concept entered.
Yeah. Mm-hmm.
That's a very important distinction, because why the force itself was taken as a parameter, because they could have taken anything else also. It's a they are all studying movements, that's all.
Mm-hmm.
It moves. Why force itself was taken as a reference? Like you said, absoluteness, in another word, it's called invariance, which doesn't
Okay.
change with time. So when they looked, you sometime back mentioned about Galileo's experiment, inclined plane experiment, where he tries to roll down objects
Yeah.
and study. So, at what point he was seeing that with time, something the movement is not constant over the first difference of time, delta t. But he was seeing that the movements were constant over second difference. That's how the G came into picture, the gravitational constant.
Okay.
So the second order variation was a constant. That's why we still, okay, mathematically we say dx square by dt square for gravity, for acceleration. So the second, that gravity invariance was used as a reference. So they thought they have reached the limit beyond which it's invariant. Everything is, so absoluteness was reached.
Okay. Okay. Oh, okay.
So they were happy with it. But then, like you said, now they found a lot of paradoxes. Huh? So they were looking for still better absoluteness.
Okay.
So we keep improving our absoluteness. So that's what is.
Oh, okay. Okay. Excellent. Thanks. Thanks, Prasanna.
Okay. Yeah. And just one more thing. As you said, imagining a curved space is slightly difficult because we see space as a three-dimensional entity. And we are hard to imagine for anything to curve, it needs one more dimension.
Yeah.
For example, a line, if it curved, it takes 2 dimensions actually. You have to draw a curved line. You need X and Y.
Right. Yeah.
So one more additional dimension is required.
Okay.
So to curve a 3 dimension, we need 4-dimensional space, which
Yeah.
many people, most of us are not being groomed to imagine from our student life.
Yeah. 4-dimensional space, and then in all Einstein's equation, we have time also as one of the dimensions.
Yes.
So
Yeah.
yeah.
So
So
you
it's
can
always.
reduce it. You can always reduce it to 1-dimensional or 2-dimensional condition. So you have one more dimension to imagine.
Yeah.
Then
Yeah.
you can expand the imagination for a higher dimensional space.
Yeah.
For the initial, that's many people we try to give the direction to imagine curvature of space.
Yeah. Yeah.
Yeah, that's one. Thank you.
Thanks. Okay. Everything was fine. And then, of course, world has coming up with the different ideas. Sorry. Yeah. So while this is all going on, lot of experiments on this quantum level, atomic level experiments happening, and Thomson discovered electrons in 1897, and atom was confirmed by Einstein's Brownian motion, and we know that particles are there across around the atom. So nucleus was discovered in 1911, and Bohr. Now that question of how does all these things are there together, right? So Bohr first produced a atomic model in 1916. If you see this diagram, this is Bohr's atomic model. I took it from Wikipedia. So he said that there is electron can be here, electron can be here. This is one energy level and another energy level. In between, electron cannot be there. That is what this model predicts and proposes. In between, what will be there? Whether you can, can the why not an electron can be there? Can't be there here. Bohr does not have an answer, or the answer is in. It's like this. It is there is no space here. Can you imagine? There is no space for electron to occupy. Then what is there here? We don't know. So electron can be either in this level or in this level. So he, in a way, he did a space quantization itself. Space itself now quantized. That means space is here. It is not continuous. Space is here. Then there is nothing here. There is space is here. So any object which occupies has to either be here or be here or be here. Cannot be in between, right? So that is how he quantized, and he came up with this model, hydrogen model, and which occupy, and in fact, this became later, this was a very simple model. Later, people have enhanced it. But finally, there was this model of nucleus is there in the center, and rest of the things, nucleus is nothing but nu nucleus has proton and neutrons, and electrons are around this somewhere here. Again, it is not a path. It is somewhere here. We will come why it is not a path. Because of uncertainty principle, we will come a little later. So, but this new with all these ideas coming and giving the next step, which is major step forward, is the way of or a description of the atomic model. Okay, the wave and particle thing continues. So we also know that we know that Newton already told corpuscular, and Huygens talked about wave theory, and Young with the Young slit experiment in 1801 shows light is wave. Maxwell equation shows that light is wave. Einstein's photoelectric effect shows that it is particle, right? So how was this summarized or synthesized? So this is called a wave of somebody coined the term called wavecle. So wavecle, we all saw that he proposed our Planck's energy formula is E energy equal nothing but it depends on the frequency and it comes in a pocket. This is our quantum's formula, simple formula, and we know that E equal to mc square from Einstein's simple mass energy relationship. De Broglie is another French scientist. In 1924, he E equals h nu, he equal to mc square. He calculated hf equal to mc square. With that, he arrived at this formula. Lambda equal to h by b. Lambda is wavelength, which is nothing but 1 by f. Wavelength is nothing but frequency's reciprocation. And is Planck constant. P is equal to mass into velocity. Mass is you have only for particles. Velocity of the particle. Mass into velocity is nothing but momentum. Right? So don't worry about all these technical details, but he gave that every particle or every mass or every material has a wave associated with it. So that is called, that is how he synthesized the wave particle fight. So they are not just two different things. They are matter's existence itself has a wave associated with it. That is how it is synthesized. And later some journalists called it as a wavecle. Okay. So that is how that next step comes in. Of course, we all know that later this wave itself, the measurement itself is a problem in the when it comes to quantum mechanics level. That is because of its minuteness or whatever the reason. I mean, I will say like I'll try to explain it like this. Say you have an electron here. You want to observe this electron. So you calibrate a grid like this, right? You try to, how do you observe? You put a light here and try to see through a microscope. Let us say there is a microscope here. You try to observe, but light itself is very comparatively almost equal for the size of electron, right? So when light comes, hit the electron will move, isn't it? So when you observe, will you really observe the electron was it here or here? You don't know. It is very difficult to predict exactly where the electron is or was. So that is what Heisenberg took it and he put it in a mathematical form, and it proposed this position or momentum of a particle cannot be accurately measured. So you can either say You can either say it is here or it is here, but you cannot say how did it come here. Will it travel at the speed of light, at what speed? All these things you cannot tell. It could have come like this, could have come like this. All these are possible because we do not know what is in between. First of all, Neil Bohr already quantized space, and this guy is already telling that when you hit a photon, it could have dislodged it. It could have come like this. So all these are possible, and then it all put together in equation, and that's how our uncertainty principle arrives. Okay. So now what happens to the atom? Atom is there. You have a path here. They thought during Bohr's model, they thought that there's a path here and electron is here revolving around. But that is all gone now. Heisenberg shatters it, and then electron can be here, or it can, now we have a wave for this electron. This wave can be like this, right? This is called standing wave, they said. And then electron can be somewhere here, somewhere here. Okay. Now this wave is actually described by Schrodinger's wave theory. Schrodinger came up with the same description of atom and energy equation, which describes actually a wave, right? So his wave can be described by this wave, electron wave. So both are fighting actually. Both were describing quantum mechanics system, and both were describing in a different way. But both were, people are already come comfortable with the wave idea, so they were going with that. Now, what is then actually oscillating here? When uncertainty is there, what is then actually oscillating? So they came up with something called probabilities. It is nothing but probability. That is, this wave describes nothing but the probability of finding an electron in this place. Nobody can tell that electron is here or here. It says that if this wave amplitude is high, this means probability is more here to find the electron here. So quantum mechanics completely shattered the idea that brought from classical physics, that there's a deterministic world, absoluteness, everything of the physics, classical physics collapsed. Okay, now when it goes to the quantum level, you have to take care of uncertainty. You have to take care of, and already we have this Einstein's absoluteness, Einstein's relativity, which destroys absoluteness. So everything deterministic was gone. So that is how the new physics evolves. And they all, it's all going on and on and on. We still have this uncertainty principle going on. And we know that quantum mechanics put together entangled particles, which is used in quantum computation and all. We know that we can study that in separate sessions. Okay, but then then they talked about now the atomic and atoms and all are in place. There are different types of forces to explain this, right? So we have these 4 types of force they categorize: strong nuclear, electromagnetic, weak nuclear, gravitation. Strong nuclear is nothing but gluons exchange inside the nucleus. This is a very strong nucleus force. When an atom smashed, when a nucleus is smashed, that is where that energy is converted in, sorry, that's where that force is converted into energy, and that energy is huge. That's called our atomic energy, right? So strong nuclear force, when it get released, that is huge energy. So that is what the strong nuclear. Electromagnetic is a photon exchange by electrons and all. Electrons with electrons are around the nucleus, right? So there will be an attraction with the positrons which are inside the nucleus. This attraction is described by electromagnetic force. And then there are some boson exchange, which is described by weak nuclear force. All these different forces, and of course there's a gravitation. So all these different forces are categorized and put together as a one. I mean, it is categorized. Okay. Now there is a huge. You all know that Einstein wanted to come up with a unified field theory or unified force field. He wanted to integrate everything. That did not happen. The world currently already integrated these three. Okay. Gravity is still, as described by Einstein, gravity is still away. So gravity and all these other forces are explained with quantum mechanics still has a problem. There's ongoing efforts to try to integrate this. That's why we have string theory, which is yet to be proved. There's a lot of math. It's just more look like a mathematics than physics. So we don't know whether this string theory will come into reality and all. And one more thing to notice is this bosons, photons, and all for each force or interactions. There's a particle involved, right? Exchange of particle was the reason for this force or interaction. So far, all these particles are existing. But we did not see a particle which is causing gravitation. So they named it something called gravitons, but this is not yet observed in reality. All others are already noted in the particle accelerators, but this is yet to be seen. So there are a lot of questions like this still exist in the physics, and we all know we don't know when these things will be answered. Okay, that let's go to the computing. Any questions so far? So these are all, when we see from 1930, there's a lot of papers, new ideas on quantum theory. They call it a scientific revolution time. This is so. So while this is going on, so all the electronics emerged, which all set the path for the next step. Of course, physics is going in its way, but which gave a very important next step is our computing field. There are two important ideas. We all know that Turing machine. We all know, we have talked about or some uh, um, school syllabus. Some college things talks about this Turing machines and all. But there are two important things which this colleges does not talk about. Is this one is that the invention of transistor in 1947, right? A transistor is something that is a major step forward towards towards becoming creating an electronic device. That's one. And in 1948, this is something I don't know whether the electronics and communication people read, but at least in computing subjects, we haven't come across. But I think this should be included in the theory papers of computer science. So this is a mathematical theory of communication. It's a very, very important paper submitted by Claude Shannon in the year 1948. So what it is talking about is the first time information is quantified. This is the paper describes how you can, basically this paper about how at that time the telecommunication is evolved, right? Already telecommunication is there in the form of wired transmission from one place to another, but this has been continuously improved. And Shannon was trying to quantify how much he was into this what is that performance tuning experiment, right? He wanted to arrive at what is the maximum capacity of a line and how much information can it transfer. So the information quantification is needed, and this kind idea of bit and byte evolved from this paper. And so he also expressed information is expressed in terms of logarithm of probabilities. We already saw some time back about this entropy. So he linked the information to entropy. This is a nice, funny idea. Say, let us say, in a string, let us say, continuously like that, right? So when you see this string, you see that, oh, nothing great, so all are yes, right? In a rainy season, you know that, okay, today it's going to rain. Tomorrow it's going to rain. Tomorrow again it's going to rain. If I come back and say that, hey, day after tomorrow it's going to rain, you may think that, oh, okay, this is not a very useful information. Anyway, I know that, right? So when it is uniform, that means when it's uniform, there is not enough information. In the same time, when the string is like this, A, X, T, V, Z, Z, C, something like that, right? That means this is random, and that means it's more information, right? So but if you see that that means it's chaotic. According to second law of thermodynamics, we said that entropy is always increasing, right? So when it's maximum entropy, it is chaotic. That means it's more random. That means it's more information. So this guy is linked the entropy to the information. So we thought randomness means we usually think that randomness or chaotic means it is not information, right? It's garbage. But actually, more randomness is more information. That is how this paper describes, and it gave the idea of measuring the information. With that and combining with this transistor, gave a leap forward to arrive at the computing. And then we all know that rest of the history. Technological developments move so fast, and gadgets we got. Communication become very easy, and copying became very easy. Right? Copying became very easy. One of the important thing that we need to note about is there is a conflicting situation now. For example, when the printing technology came in 1700s, it is almost now 4,400 years old. In 1700s, when the printing technology came, they came up with the copyright law, right? When I have a book published, I don't want somebody else to copy. Or when I have a music itself was not digitized at the time, but slowly it became magnetic tape and all came. Now, who will copy this book or tape and all? This was protected by copyright law. But electronics became very, very sophisticated, and copying became very easy. All you need to have is a pen drive now. The very younger generation, they don't even need pen drive. See, when I was in college, we were using CD. When I was working, we use pen drive. But my sons do not even use pen drive. They use Bluetooth, transfer music from one file, one place to another, or do a FTP, copy the file. All these things, they don't need even pen drive, right? So electronics development is in such a way that copying became very, very quick, cheap, and massively you can copy. Now we have this very old copyright law. The society says that, oh, don't copy, but technology says that, oh, you can copy, right? When I described it to another student, she asked a very nice question. Sir, I have a question. Okay, I told, okay, shoot your question. She said that, okay, I have my computer, I have my CD or pen drive, I paid for electricity, I am sitting at home. Who are you to say not to copy? Right? I don't have that answer. So do you see the conflict? The society has a conflict now. That's why in the olden days you might have seen this in the table in the roadside they will put a table and put lot of pirated CDs. Even today you can see that lot of nice books, pirated books sold in the roadside, right? So there is we call them pirates, but technology gives a nicely the way to copy it. So there's a conflict here. Who is really? Is it really? As this student asked, is it really stealing? She did not agree. So that is what this next big idea came from free software. So this is a philosophical understanding. So what this is talking about is there is a conflict in the society. It's trying to address it in a nice way. So they software becoming more and more like a like mathematics, right? You cannot avoid using mathematics in your life. You may not be a mathematician, but you will be continuously using it anyway. Like the software has become more and more, in fact, nowadays more and more important than mathematics. Everybody is affected by it. So the idea of free software is nothing but use this software to use it for any purpose. Understand, you can understand it. That means if you're writing a program in C, C++, the source code should be available. You should be able to modify and you should be able to redistribute. You can redistribute to anybody, right? So that kind of all freedom, it guarantees you the freedom to use, understand, modify, redistribute. That's how society can survive. That's the philosophy behind this free software, which is nothing but addressing a social conflict of copyright and the electronic fast development. The law is still very old, but the technology has become super fast. So software has given the excellent this kind of uh, a way of thinking which gives you to share. It's enabled to share, right? That is how the internet and all became possible. All the internet, like the code is from BSD, Berkeley Software Division. All internet code, including your closed source software like Windows operating system or Mac OS uses this free code for the networking purposes. So connection between the human minds through the computer became all possible, and that's how free software takes the technology to completely to a next level, right? And so you know that now software is something that a code that we write, people can improve it. But what happens to a painting or a movie? You cannot you cannot take it and change it, right? A person painted, the painting is going to be like that. Or literature, we don't want to change it, right? The other works that follow this is the derivatives. These kinds of things which you can freely give, publish, is taken care by a license called Creative Commons. So Creative Commons license is there for arts. Free software license, we call it GPL, General Public License. Or there are a lot of different licenses is there for software. So software and Creative Commons, free software and Creative Commons gave a one more freedom or a way to see how you can create, use, distribute, right? So that is how that went, and we all know that this all went further and further, and we have now neural network computing, which is creating an artificial intelligence tools like LLM, and we are using now even ChatGPT and deep DeepSeek, right? DeepMind. What is that tool? So we are using all those. But of course, the mathematics of this is there from 1970s itself. It's going on. But don't worry about too much about computing. Sorry, this artificial intelligence. For example, I noted this nice picture. when somebody took it to asked LLM to draw Mother Teresa fighting poverty, it came up with these kind of pictures. Okay, so it's funny, but I just wanted to point out that learning by computing is not like learning by humans. This is a different way of. This is nothing but a pattern matched learning, right? I was reading this book by Gary Kasparov when he played the um, what is it? Deep Blue chess player. His suggestion or his way of expressing it is it's lot of millions of records of each player is put in this server. It actually is more a search and pattern searching and finding of the moves, not the intuitive learning. So now the question of learning itself is um, kind of redefined, right? We thought learning needs consciousness. Probably learning probably does not need consciousness. It looks like learning can be in different ways too. That is what currently going on. But still, this kind of learning is still has to be refined. Let's not worry about it too much. Still, there's a long way to go in the artificial intelligence. But it is going to be unavoidable. It's going to come. What kind of impact it's going to go give in the society, it needs to be seen. So the question now, I want to leave the session with this question. Does learning need consciousness? Maybe not, or we don't know. We will see soon. So that's what these books helped me to arrive or to put together these sessions. Yeah. So that is what I wanted to discuss today. Any question?
Once again, one observation regarding the Shannon.
Mhm.
Uh, though it's a very beautiful pair. I too have gone through a bit of it, but it's so pervasive. Last week I was trying open source software, audio software, Audacity. Many of you might have heard.
Audacity, yeah.
If you try to record speaking to that
Mhm.
in the recent version, like you mentioned, the same, if you keep doing it, initially it records, but
Mhm.
after 2 3 seconds, it starts reducing its amplitude and slowly filters it out completely. So
Yeah,
even if you, so interestingly, it doesn't see it as a information; it see it as a noise.
yeah.
So how nicely they and you have to force yourself to record music. You have to change inside some settings to record it.
True. Actually, that is how this compression mechanism works. Say, I'm just trying to use it very simply. Say, if you say 10 years, it's up there. It needs 10 bytes to represent this 10 years. Instead, it will say 10A, right? There's an algorithm which will compress like this. So it will need only 3 bytes, right? So
Okay.
when you create a zip file, I'm just doing it very simple, simple algorithm. Sorry, simple way of telling. But there's a complexity on this algorithm. But basically, it tries to gives a statistical number to each word, and if multiple such words come, it tries to reduce it, and somewhere it will tell that here instead of this word, you just replace it with something else. So it will give a smaller number or some indication to those words. The more frequency of the word in English, the more the lesser size of that replacement character, so that it will replace it. But
Okay.
crudely speaking, it is replacing it like this. That is
Okay.
what this algorithm probably following.
Yeah. Thank you.
Thanks, Prasanna. Any other question?
Nothing is, I had never easily understood that what is Creative Commons, and today I couldn't get that in a very
Okay.
straightforward way. Thank you for that. Of course, many other things I learned today, but then this is something what I had never put my.
Okay.
Thank you.
Yeah, this is a very important thing coming up right now. See, I say this, my wife is a freelance photographer. Whenever she publishes something, people will take it. Just they will not even give credit. They'll publish it somewhere. And as if they think that it's their photography. They will publish it as if their photograph. So it's better to publish it with a license, right? So that people can, so you can easily copy anyway. We cannot prevent it. Instead of worrying about it, there is a way you can put things together. You say that Creative Commons. There's a multiple attributes to this Creative Commons. So one is that you can say that Creative Commons for all free purpose. That means the other person who is taking your work, if he or she publish it or use it for non-commercial purpose, it's free. For commercial purpose, you have to he or she has to share some common profit to you with you. All these are possible in this Creative Commons. They have multiple attributes, so you can publish it like that. If you just publish without any license, then people will take it. They will say that you can't even go and do some content. So that you cannot go and argue, fight, because if you don't want to be copied, don't publish. Right? That is the attitude nowadays. The moment you put it in the screen, people will copy.
Got it. Yes. Thank you.
Okay. If there are no more questions, I think this is our last session. I mean, this is nothing like comprehensive enough. There are a lot of things to learn. Please shoot out to me in the group if you have questions. I will always be happy to answer. Thanks for patient listening and cooperating. And thanks for the opportunity. Thank you very much.
So this is the last session, Balaji?
Yes.
Oh, okay.
I came till this artificial intelligence group. What else should I cover anything else?
No, I think we're done.
Yeah. So far it has become 8 sessions, Guru. One is done by Judah. So
Correct.
we have to modify the course title, not just by Balaji. You have to put that
Sure.
put Judah's name as well.
Yeah.
So, and I think all other videos are there in place. This will be added too.
Okay.
There's some very nice video I saw regarding analog computing, Balaji. Have you seen that?
What is that?
Analog computing?
No.
I'll put a video up. Apparently, that might be the future of computation. So it's very similar, like how the neural net computation works. People have a kind of an analog, what is that? Analog variant of that.
Yeah, we do analog computation, right? Personally, humans do analog computation, right?
Yes.
Okay. Oh yeah, please share it in the group.
Definitely.
Yeah. Okay. Thank you very much. Thanks for the opportunity. See you all. Happy reading, happy learning.
Thank you. Thanks for Balaji.
Thank you.
Thanks, Balaji. Yeah.
Mm.
Bye.